I had this vague impression that I'm either scaring people away or serious slacking is underway already. I don't know which. It seems like our number is slightly diminished, but the class is large enough that hopefully that won't be a problem for me, because it would be fun even if there were 10, so it's okay. Okay, let's see. So I guess I have my standard rant about procedure, and that sort of comes to place today. So I'm thinking, may not matter what I'm thinking, but I'm thinking that you will proceed. The normal way to proceed is you will have done the first homework by now, and that most of you actually, I mean, at this point, at the very beginning, it's not so clear, but certainly after the second or third week. But I mean, the normal thing to do will be to have done the homework now, looked at the solutions, and the normal thing will be that you're mostly okay, but you still have some questions about things or you're not quite sure. So the normal thing to do, and I'm not sure what you'll do exactly, but the normal thing to do would be to go to the recitation at 1 o'clock, and the TA will talk about all that stuff and you'll learn more. It's just like I'm talking about problems. So I'm going to today talk about problems in the book and so forth, and elaborate on it and hopefully help you understand. I mean, you could be doing this all on your own, but I mean, hopefully listening to me ranting about these various things will help you. And in the same way, I hope many of you will go to the recitations, because that too will help. Because even if you've done the problems, unless you're totally sure, if you're totally sure, and that might well be the case at the beginning, but if you're totally sure, probably you don't need it. But actually, if there's some issues still, it actually could be very valuable just to hear somebody else talk about it. And it may be more valuable even after you've done it, unless you're totally sure. If you're pretty sure, it can actually be very valuable to confirm your understanding, even if you mostly understand it. So I'm encouraging you to follow the normal pattern of doing the homework on time, going to the recitation, and then the homework would be collected on Thursday. And I'm assuming most of you will turn it in, even though the grading, I've been very upfront, the grading is primarily performance, exam performance, and there's 3 exams, so it won't all be in one batch. But anyway, I'm thinking that the normal process will be good. And well, I'm expecting the first recitation, the first 2 homeworks not to be, the first one certainly not to be too hard, but certainly if you find that the first one is not totally clear, you should really think of coming to the recitations, because I'm sure they'll help. So that's putting in a plug for Ieorertsj, who will, it is a little sudden to come from this class to start coming to a recitation at 1 o'clock, but at least there's a chance to have lunch in the middle. Okay, so I want to talk about a few problems, and I've picked out, so I'm moving forward. I'm thinking about assignment 2. You should have been done with homework 2, but you're still sort of thinking homework 2, first homework, I'm thinking about the second homework, and so I'm moving on to the material, in class, I'm moving on to the material that would be related to the second homework, and I want to talk about problem 3.3. Actually, these are the examples. So I'm actually talking about the example in the text. So I'm going to do talk about these examples. So I'm not even doing and now last time I did last week I talked about exercises at the back, but now I'm talking about examples. And this example says, let x and y be independent Poisson random variables with means lambda 1 and lambda 2, and then find the expected value of x given x plus y equals n. Now, actually, the point I want to make here is not so much about how to do this problem, but that's also good, but like sort of making sure that even before you just do the problem and have that, there's a whole lot in this problem that you would want to understand, should understand from probability, but might have forgotten possibly. There's actually a lot in this problem that you ought to think about carefully. So the first issue is what does it mean for some x and y to be a random variable? Okay, that's a major issue actually. Stuff just there, the problem is there, but this is actually an issue. So this is, for the most part, there's two sort of definitions to have in mind. For the most part, when you talk about something being a random variable, x is a random variable, usually denoted by capital X, capital Y, they're random variable, it's something that has a probability distribution, right? So instead of just saying you have a random experiment with this probability distribution, you talk about it in terms of x. So x is a random variable with a Poisson distribution. That just means that we talk about probability x equals k, and it has a Poisson distribution with parameter, it has mean lambda 1, and that's its parameter. So this is the Poisson distribution, right? So x is a random variable when we talk about it that way. X has so the probability x equals k is this Poisson distribution, and the Poisson distribution has its mean, this parameter lambda 1. So this is for k equals 0, 1, 2, so integers. So this is the Poisson distribution that came up as the approximation for the binomial when we talked about that before. So we're kind of relating to what we did before. Okay, the other part of this, there is a very, Ross does a good job of keeping this really down under the radar, the math. It is actually somewhat helpful to remember frequently that this is the probability is a branch of mathematics and it has definitions and axioms and so forth, so that things have precise definitions. For example, when you deal with conditional probability, it's not what you feel about it, there's a precise definition. And that was the whole point of the first lecture, that if you know that definition, apply the definition, everything's straightforward. If you think it's an issue of how you feel about it, and the definition's fuzzy in your mind, the whole thing becomes fuzzy. So in the same way here, it's good to have, it's helpful, but possibly confusing, to understand how a random variable fits into the probability mathematical model. And it does so in a very simple and explicit way. So you assume the standard part of the probability model is you have a sample space and a probability measure. This is sample space, probability measure. Like if we did 2 coin tosses, it might be head, 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 tail, tail, head, tail, tail. And this is a set with 4 outcomes. That's the sample space. The probability measure attaches probabilities to subsets of this. That's the formalism. Now, a random variable is very simple in this context. A random variable x maps S, a real valued random variable. It just maps some, not just this one, but some sample space, some probability space into the real line. And it will thereby induce a new probability distribution over here. So the probability that x equals k formally is the probability. Now, probabilities really attach to sets, events. So this probability is really going to attach to the set. This is the p here. There's a p here on this S. So x is a random variable. There's a sample space, a probability measure given in the background. We never mention it usually. I never said what it was. This is kind of a confusing formalism, because when we talk about these random variables, usually we never mention the underlying sample space. We don't care anymore. But it's there. It's sort of there in the formalism. There's some space with a probability measure on it, and x maps it in the real line, and then this is going to be the meaning of this. It's this probability measure on some subset of this, and it'll be the subset of that such that it's the obvious thing. This is interpreted, the probability that x equals k is interpreted as the probability of a particular event here, a subset of this, and it's the subset of S in this sample space such that xs equals k, just what you'd want. But this is the formalism behind it. Whenever you see a random variable, it's understood there's some underlying space. This is just one, this is not, of course, the general. This is just one example. But the formalism has that there is a sample space and a probability measure on it. Whenever you talk about random variables just map some sample space and give you a new, and so there's a distribution of this x. So for practical purposes, it's true. Most of the time, you just think, when you're talking about a random variable, it's something that has a probability distribution. And then we would have written it out. In this instance, it's Poisson. So I'm just emphasizing what is a random variable. Okay, that's Ross says this. Ross does a good job in this book on focusing on examples and not getting too bogged down. So he'll say this just in the, you might, if you read, you have to read carefully to even see it. So it's kind of like the formalism is minimized, which is good from an engineering point of view, but it actually is, it's actually helpful to understand the formalism because someplace it'll come up. Okay, so that's the business about the random variable. Now, the other part that's said here, well, we've talked about Poisson, and here's Poisson. The other part is independent. So actually, all the stuff that's written up there, it's sort of really basic to probability, but you want to understand it. You don't want to be vague. I mean, when you say x and y are independent Poisson random variables with means lambda 1 and lambda 2, well, here's what the Poisson part is, the Poisson random variables. We haven't got to independent yet. A lot of this is to be absolutely clear what these things mean, which you would do in the basic probability course. So we want to know, what does it mean for x and y to be independent? Now, we've already focused on independence of events. We talked about the conditional probability of A given B, and that's, by definition, probability A, B over probability B. And independence occurs, A and B are independent if probability AB equals the product, okay, which is the same thing as the probability A given B is just the probability of A. This is kind of a nice, natural, intuitive form, right? The conditional probability of A given B is independent of B. So that's a natural way to think that A and B are independent. And similarly, the probability of B given A will be the probability of B. And that's just equivalent to this because this is the definition. Okay, we've been through this. But actually, that does not entirely tell you what it means for two random variables to be independent. And you want to know the difference because you know that it has to do with this somehow. But it's not quite, I'm just emphasizing, this is emphasizing basic probability, which all should be totally clear to you from taking your previous course, but may not be. And you're having 2 weeks, and these issues are exactly the points where you'll have difficulty if you have it. It's because the real basic stuff from the first week or two of the probability course is not firm. That's the usual cause of difficulty, because you'll do some problem, and these issues aren't clear in your mind, and you'll have problems. Hopefully, if things are shaky, you're filling this all in, and things are firming up again, and you're thinking, this cumulative aspect is pretty serious. Okay, so what do we mean about x and y being independent? These are two random variables. The distinction is, well, the random variables aren't events, right? X is, so you actually need a definition. We know what A and B are independent means. We just talked about that. But what does it mean for x and y to be independent? In other words, what does that condition mean? Well, we know that, if it talked about the conditional probability of x given some sort of y thing, it wouldn't have anything to do with the y thing. But you want to think about it this way. The probability x equals k given y equals m. This is certainly the right idea. This is an event, this is an event, and this is an event, and this is exactly what we wrote down before. So this is, in other words, this is some event. And this is some event. But these sets are kind of ignored in the notation. But this is a special case of what we wrote down here, for events to be independent. But now we're talking about random variables being independent. And the point here is, what's extra here is you're going to say this. In other words, this is one event, okay? But when you want to talk about random variables being independent, you want this independence to hold for all possible values. So there's something extra about random variables. It's not the same as events. In other words, you want this event and this event to be independent, but for all choices of these arguments. Okay? And that's natural, but there's a definition there, precise definition. So random variables by themselves are not events, but every possible value of the random variable produces events, and you want all these events to be independent. All the events to do with x and y to be independent. Not just one, but all of them. And that makes sense. You want the random variables x and y to be independent. Any events you define in terms of x and y should be independent. Okay? And that should make total sense, but there's a precise definition. Okay, given that, you might think about this. So one thing that's always good is to have when you're doing probability, part of the interest, in fact, I think the major interest is that we actually have opinions about how likely things are. And like you're playing cards, things are happening and you have an opinion, and the question is, are your opinions, are things like you think? And on the interesting part is sometimes things are tricky and they're not quite like you think, but you have an opinion. So when you see this, it's natural to think what you think the answer should be right up front. I mean, you see x and y, x is Poisson, y has a similar distribution with parameter lambda 2. X and y are Poisson. The mean of x is lambda 1. The mean of y is lambda 2. And now you're told that the sum of those two is n. How big should x be? Well, so the thought is, well, the bigger the sum, bigger x. That certainly seems right? Sort of intuitively. So I'm thinking, so you think you shouldn't just look at it and think, you have an idea. So it's reasonable to sort of think what the answer would be. You might think that an ideal answer would be somehow that the bigger n, it would be proportional to n. That would be nice. Because the bigger n is, the bigger the x ought to be. And somehow you think x, if the mean of x is lambda 1 and the mean of y is lambda 2, you might think it was something like this, because it would be proportional to the ratio of the means. That's just a guess. That's not good logical thinking. I'm just saying that's sort of up front. If things were nice, that would be sort of reasonable. Actually, things could be different for different distributions. Okay, well, that actually is the right answer. But that's sort of a kind of the thought process I'm trying to illustrate is you might just guess the answer, so then when you calculate it, you have some idea that what you're doing is making any sense. I mean, somehow the main thing is I'm thinking that it's increasing in n, and somehow related to lambda 1 over lambda 1 plus 2. These sort of things sort of seem like the right thing. Whether it should be exactly this is certainly not obvious. Okay, then actually, I wanted to emphasize that background, but now you come to actually just doing the exercise, right? Now we've come to doing it. And there's a gap here in how you approach this problem. Now we've defined everything, which is really the main point. And it's not in the exercise. The exercise just does it. So you're now coming to the part where he will give the solution. And in fact, most of the story is before you get the solution. If you're confused, it's probably because part of this background is not 100% clear. But given that it's clear, he's going to now I'm coming to the point where he's working this out for you, and he's starting at this point. And there's one idea that's being conveyed, is that when you want this, there's two steps. So it's, again, divide and conquer. It's sort of like when you look at it straight out, you think, well, what do I do? Because it's sort of not clear what you're going to do to compute this right out. I mean, it's sort of easy enough to understand what it means, but it's not clear. There's two steps. That's the standard thing you do. And the two steps are to write this first, and then this. Now, this last step is easy. conceptually, so I want to do this first. Now, the point here, this last step, is the one I kind of start here because this is the question. The point is, you're reducing this problem to this one. This is not, in other words, he didn't ask this, but this is what you want to do first. You want to find the probability distribution, the conditional distribution of x given x plus y, and then compute the expected value. 2 steps. You first want to find this probability distribution, then you calculate the expected value. If you try to do it directly, you just kind of don't know where to go. So once you think, I'm going to do this first, now 2 is then easy. Why is 2 easy? Because this, a conditional probability distribution, is just another probability distribution as a function of k. So the expected value is just like always. The expected value of a random variable is the sum of the possible values times the probabilities, summing them up. This is a conditional probability. It's just a probability just like any other one. That's the important thing to know. When you see a conditional probability distribution as a function of this argument, it's just another probability distribution. Conceptually, this is some sort of probability distribution affected by this, but it's a probability distribution as a function of k. So therefore, when you compute expected value, you're going to just take k, probability x equals k, and sum it. And so you do the same thing here. So this step is, that's the point to be clear in your mind, is conditional probability. Yeah, it looks messy, but this is just another probability distribution as a function of k, nothing mysterious. There's a complexity, but basically this is this. So when you want to compute the expected value, you're just computing the expected value with respect to this distribution. So the first step the problem's been reduced to is to calculate this. And once you've done that, the problem's easy. I mean, you just crank. But the thing that's confusing is when you're given this problem, you don't see that you should do this first. Okay, I mean, that maybe, I may be belaboring the obvious, but possibly not. So then when you want to do that, once you've written this down, you see this is an event to compute this now is again cranking. So this is cranking and this is cranking once you've indicated what to do. In other words, this is a probability of an event conditioned on another event. So when you do that, you're just doing this. Remember this. And then you're doing this. The point I'm trying to point out is, here's the definition of conditional probability. Here's the definition of conditional expectation. This question that looks confusing is precisely just using these 2 definitions in 2 steps. Nothing else. Very simple definitions, basic, repeated. But the step to get that calculation, you got to do the 2 steps, not 1. So you're going to do this. So that means the probability x equals k given x plus y equals n. So this plays the role of A, this plays the role of B. So that's the probability that x equals k, and now you're figuring out what that means. This is the, if x equals k and x plus y equals n, that's the same as x equals k, y equals n minus k, right? I've just translated it. And then in the bottom, I've got the probability x plus y equals n. Well, still, you're going to have okay, so you actually things are not quite so simple, but let me, because there's still there's some things to remember. So once you write this down, you're in pretty good shape. You have this thing in the denominators. You actually have another step. But the first thing is the probability x equals k, y equals n minus k. Now this is where you use the independence. Because you assumed x and y are independent, so this is going to divide. Now you're left with this. And you have to know how to do convolution in the denominator. But all I've done is, so far as I've gotten the numerator, I've just said this numerator, because this is x and y here, the independence means this is going to separate into the product. So then you're left with this independence. So the denominator. And then this, of course, if we wrote this out, this would look like this. So then we're left with calculating this. Okay? Yeah.
Why did you do y equals n minus k?
Remember, when I'm doing this, this is the probability of the intersection of the event. So I have x equals k and x plus y equals n. So if x equals k and the sum equals n, y necessarily equals n minus k. So that's equivalent to this. I could have written the product of these two. I did two steps at once, because the intersection of these two is equivalent to this. And then that's where I want it, because I've now got x and y separate, so then I can write this way. When I've written it as terms of x and y separately, I can factor, and I've got this. Okay? Yeah, and I probably, in fact, I'm violating my principle that if you separate the steps one at a time, indeed, by doing two steps, I cause some confusion. So indeed, thinking, not jumping too fast, doing things step by step is actually better. There's some point where you lose patience with that if you see what's going on, but it's very important in clear thinking. Yeah, go ahead.
And that step, if you had probably an AB, if you put it as...
Yeah, this is A, and this is B. And therefore, this is this, but with two steps. One to write, I should have written x plus y equals n. First step. That would have been doing directly this. And then I would have said, well, this is really the same thing as x equals k and y equals n minus k. Inside. And I did two steps at once. I should have just routinely put whatever was here inside here, right, like that. Then done the second step. I mean, that's not too much of a crime, that particular part. It's sort of like when you start with this, if you try to do this straight away, you don't get anywhere. I mean, nobody gets anywhere. Sort of, you do these, you've got to sort of break up the pieces. So when you do this, here you come to the issue of what this means. This is how do you compute this distribution? And this is the probability that x equals k, probability y equals n minus k, summed from k equals 0 to n, right? The probability that x plus y equals n, well, x and y are independent, so actually I could have written this way. This would be better. The only way I can get x plus y to be n is if x is k and y is n minus k for some k, and I add up all the probabilities. So this event is by definition this. So I'm breaking this down into what its components are, and then I can factor this just as I did above, and then that looks like okay, and what's happening here, so this part, we've got algebra here. We're reducing this point, I've used this, and I haven't even got to this step yet, but I'm just writing this all down, and I've actually taken the numerator and the denominator, and the numerator is this, and the denominator is this. Okay, and now I've got all this stuff that's got exponentials and powers and all this stuff, right? All this stuff is sitting here. So this point, algebra. Okay, now let me just sort of comment. I mean, that may be an issue. In some sense, like on an exam, well, you're most of the probability part of what is that, that's this divided by this. minus the algebra. Part of the problem is, well, how does that simplify to understand what's going on? And this is something you then learn as a high level. So let me comment on the high level, but that's what the algebra shows you. But I'm not going to emphasize this. I mean, at this point, the answer is this distribution. Let me put it here. The probability x equals k given y, x plus y equals n, equals e to the minus lambda 1 to the k over k factorial times e to the minus lambda 2 to the n minus k factorial over, let me sum, let's pick j, e to the minus lambda 1, not to confuse this k. This is what we've done so far. And this thing is down here that we found is the probability x plus y equals n. And this is the probability that x equals k, y equals n minus k. Right? Those are the numerator and denominator. I'm just summarizing what we did. Now, the thing you're going to find from the algebra, rather than just barraging you with algebra, I'm thinking where you get to the point. This point, it is algebra. But what I want to emphasize is that if x is Poisson and y is Poisson and they're independent, then x plus y turns out to be again Poisson with the sum of the means. This is what this algebra will say. So this is going to be, this thing is going to be this. And this is where you've memorized it. I mean, this is where knowing this fact is good because you could screw up the algebra. Okay, but this, if you do this, it'll come out to be this. Well, you see right away that e to the minus lambda 1, e to the minus lambda 2 is going to come together as e to the minus lambda 1 plus lambda 2. You certainly need to remember all the stuff about exponentials, right, and sums and all this stuff. But this numerator, this piece, the probability that the sum is n, the sum is Poisson with the sum of the parameters. I'm just skipping the algebra, telling you the bottom result. But that's a good thing to know. So you'd know the sum is Poisson, and so you would have written, so if I go back here and write all this down now and use that fact, but the algebra is there in the book in a previous problem, but you would then have, I've simplified things, but you get e to the minus lambda 1 to the k, e to the minus lambda 2 to the n minus k factorial, k factorial. And now you get down here, this simplifies to e to the minus lambda 1 plus lambda 2, and then lambda 1 plus lambda 2 to the n over n factorial. This is the bottom simplified by algebra. Now you see that things cancel, and you're looking at, if you just rewrite this, the algebra looks like this. In other words, the exponentials all cancel. Here's lambda 1 to k, lambda 2, but if this has got all this, so you put k of these with this, and n minus k with this, and you get this. This is just the algebra. I'm giving you the result of the algebra. I'm not doing it slow. Just giving you the result of the algebra. The important thing is to know how to interpret what you see. There's a simple story. What is this? Yeah, it's binomial. This is saying that, first of all, the sum of two independent Poissons is distributed as Poisson with the sum of the means. Nice thing to know. That's the kind of high-level thing to know. This is what the algebra will show you. That's the denominator. Okay? Sum is Poisson. But the conditional distribution of one Poisson given the sum is binomial. Here it is. Algebra will produce it. But of course, that also is good to know. So that's a kind of fact that you would know, so you anchor what's happening. And well, okay, what's the mean of this? The mean of a binomial is NP. N, and the P here is this. And that was our guess. Things don't always work out like that, but Poisson and binomial are really special, very nice, good things happen. So all this you crank through all the algebra, and because of these nice forms, everything comes out beautifully. Sums of independent Poissons have a new Poisson distribution. Conditional of one Poisson given the sum is binomial. And therefore, the mean is just the mean of that binomial, which turns out to be this, because the mean of the binomial is NP. Now this is sort of like, if you don't know that fact, you're stuck with doing all the algebra, right? I mean, how do I know the mean of the binomial is NP? Okay, you have to sit down and here is the binomial probability. Here's K, here's the mean. Algebra is going to show that this is NP. Okay, that's tedious. To some degree, you want to just know these things. I mean, you don't want to sit there and rederive all this algebra. I mean, you should be able to do it, but you're just knowing that. So in the background. Okay, but that's this guy. This is reviewing things about the Poisson distribution, the binomial distribution, what a random variable is, what independence is, and so forth. There's a lot here, a lot of background here. Okay, let's move on. Let's see. I have in mind doing 3-6. I'm not moving very fast, but it's okay. It's okay. It's much better that I not, as much as possible, not have firmly in mind what I'm going to do, or I'll really get crazy. And if I think I've got to do the problem in 2 minutes, it's likely to be totally nuts. Okay, so 3-6. We have some density. We have a density. So this is again example. And we have here, I guess we could have random variables, or we can have a density. So if I have random variables x, y, but they have a density. And it is and this is for so you could have not put this here, not have, if you have random variables x and y, this is how you would denote. Otherwise, you just leave these subscripts off, but you have this density. So it could have been just written this way. And the density, so that means that you're sort of sitting here, 0, 1, here's x, here's y, 0, the square. This density is defined on the square, and this is the value of the density. So the idea of the problem is x and y is a pair of random variables. Therefore, the pair of them, x, y, is a random vector in the plane. And in particular, it's in the unit square. So this pair assumes values in the unit square. Okay? And this is the density. So this is the full description of the probability model. The density of x, y, assuming the value little, this is little x here and y, little y here. The density at this point is given by this. Okay. That's the claim. How do we know this is all right? What do we need to have this thing make sense? I mean, did he define, it's in the book, it's the 8th edition, surely it's correct, okay? That's pretty safe. Unlike most books, the errors in this book are way lower, because it's the 8th edition. If you get a 1st edition, you spend half your time wondering if you see something that's done incorrectly. So this is actually a nice thing about this book. So okay, one logic is, well, it's in the book, it must be right. And that's not bad. But the thought is, well, a probability density is, now, this is, again, the issue is, what does this mean? I mean, a lot of the background is the important thing to worry about. So one thought is, suppose we talked about this. to focus on what this means. It ought to say something about this. So what's the probability that x is a half and y is a half? That's right here, right? That's this point right smack in the middle, right? What's the probability of that point? Yeah. Loud and forceful, unambiguous, not hesitant, 0. But this point right here, right in the center, has probability 0. What about this point over here? Zero. Okay. Now, isn't there a little bit of a problem, potentially, an issue, that you ought to be 100% clear about? There's an issue here. This point has probability 0. This point has probability 0. Every single point in that square has probability 0. Doesn't that suggest there might be a problem? If every single point has probability 0, and you add up all those zeros, what's the probability of the entire square?
1.
Well, it's either 0 or 1, or maybe a half would be a compromise, right? A half would be a compromise, right? This is a fundamental issue about math, right? It's a math that has to do with densities and a whole thing about integration as opposed to sums. I mean, this is all about calculus. There's all this stuff of what you mean, okay? So the probability of the point, the random point in this square anywhere is 1. And, well, we could compute the probability that it lies in any region, in any set, like, for example, like this. We'll have some positive number. And yet each point has probability 0. And that's you know that probabilities of disjoint sets sum up to the sum of the probabilities. But that's only for countably infinite sums. There's a problem. There's uncountably infinitely many points. All this bizarre craziness from calculus and so forth is here. I mean, you know, each point has probability 0, and yet these regions of positive area have positive probability, not points. Any 3,712 points, total probability 0. The probability of all points with rational values that can be written as fractions. That's all the points. Boom, 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 boom. They're actually dense in this picture. You know, where x is equal to m over n and y is equal to p over q, where these are integers and where they're fractions between 0 and 1. There's a lot of these points in here, right? Rational points. But that's not, the majority of points are not rational in some sense, because the probability, there's countably many of those rational points, so the probability that the outcome is rational in his square is 0. And the rest of it's probability 1. Okay, but this is sort of the math of the continuous things. So it's just like calculus. So we're actually, when we want to talk about x and y, individual points are going to have probability 0, and any finite number and any countably infinite number are going to have probability 0. But the probabilities of areas are going to have positive probabilities. And so if we want the probability of this a, this square, we would have over a. Over, this is a two-dimensional integral over a. And this is where calculus comes in, because when you compute probabilities with such things, you got to integrate. Two-dimensional integral. So you got to remember, as you're finding it, as it must be clear in every course you take, that all that stuff from the past doesn't go away, right? So to find this, you got to integrate. Okay, then when we come to this question of what is our question? I never wrote the question down, but here's 3.6. The question was that, and compute the conditional expectation of x given y equals y, and then as a function of y. So this looks just like the last problem. We're actually got some funny distribution, and we're asked about a conditional expectation. So it's the same approach. You're going to want to reduce this to first finding this. You want the conditional probability, and then this thing is going to be the integral of x, f, x, y. This thing is the conditional density of x given y, where x is little x and y is y. This conditional density. This thing is a density of x, just like before we talked about the conditional probability was a probability mass function just as a function of k. This is a legitimate density, so when we compute the expected value, it's just computing the expected value in a standard way for continuous variables, but where this plays the role of the density of x. Exactly the same idea as the last problem, only it's continuous. So the point I'm trying to make is, again, two steps. This is written this, where you first calculate the conditional density now instead of the conditional probability. Okay, then what is that? And now you need to recall the definition, which is not, it's just what you would expect. Well, anyway, f the conditional density is the joint density divided by the specific density, which is this. If you wrote this down in the form, you would have written probability x contained in x plus epsilon, given y contained in delta, something like that. You would have written this down as events in intervals, and then you'd have done some kind of limits, and you'd get this. So this is sort of a natural thing. So this is the definition. So you're in the same way, you've reduced, well, the numerator is exactly what's given. The question is, what is the bottom? What is the denominator? Okay? And so if you're given this, which is what we're given, how do we get this? The density y in terms of this is just the obvious thing. You sum out the x. Okay? So this is this, and that's how you get this. And this is just given to you. And then you just divide, and you've got this thing, and you compute the expected value. I'm just reviewing the standard stuff, but what I just did now is a continuous version of the discrete version before. Okay? This is in all the calculus is in this case, the calculus is in the book. This is 3.6. So I'm avoiding actually doing the algebra and the calculus, but emphasizing what's going on. Okay. Now, let me leave that. Okay. Now we have to do, because we have to do this every day. I think every day we have to have okay. We have to have three. We have to have 3 doors, right? We have to have 3 doors. This is where is the 3 doors come up here later. I'm changing gears. In case it's not obvious, I'm changing gears. 3 doors are 312. So we're in a mine. So you got change of, we're in a mine now. We got 3 doors, okay? There's no car, no goats now, but you have to, again, you pick the door, so now you don't, you're going to pick the door at random. But you're in this mine, and if you pick this door, you want to come out, and you want a random variable x to be the time to get out of this mine. and you want the expected value of x. Okay, now, well, I have to tell you the rules. So you're in this mine, and you want to come out, and then x is the time it takes to get out, and you want the expected value. And now, what is the rule? Well, you see 3 doors, and you actually don't know where they're going, and so every time you come, you pick them at random. Pick one of these 3 doors, each with probability 1/3. The rule is if you pick this door, you come out in time 2. If you pick this door, you come back in time 3. Now, come back means you're right back where you started. And if you pick this one, you come back in time 5. Now, you get out here. If the only way you're going to get out is to pick door 1. Because when you pick door 1, you get out in time 2 after you pick door 1. But if you pick these doors, you come right back to where you start after that time. So this process, the thing to observe is this process could go on and on and on. Because if you randomly pick a door, as long as you pick one of these 2 doors, you come back to where you started. So if you did a probability tree, let me do that here. If you do a probability tree, here you start. So there's 3 things, and each with probability 1/3. And if you do door 1, you're out in 2. You're done. If you pick this, you've taken 3, but you're out, but you're continuing. And if you've gone here, you've gone 5, and you continue, right? And then here, it's 2 more, so this is 5 out, right? The 3 plus the 2. And then this would continue. And then this would be out. And then this would continue. And this would be out. And this would continue. And this would be out. And this would continue. And this would be out, right? And then you're getting kind of ill, right? So you don't want to do it that way. So what I want to emphasize here is when you're stuck with things that are going on endlessly, you want to reduce the problem. So there's a trick here that you want to apply, which is to create an equation. And think of it in terms of not trying to fill this probability tree, which has no end and is not getting you anywhere. Yeah?
But if you're out of 3, right? And
Yeah,
you
so
come
you're
back out in 5.
this is coming back to where you started.
Where you started. Then you know that you're not going to choose that door.
No, now every time the problem is, this is a stupid problem. Every time you come back, you forget. This is really stupid. Like, you're the professor. You're not the smart student. You're the dumb professor, and you come back, and every time we do it randomly again. Or you're the mouse. We're going to come to Markov mouse later, and this is an example of Markov mouse, where every time you come back, you're in a maze, and the animal does it at random, which is also questionable. Reality. So every time, this says come back where you start, and every time you come back, you do it totally at random. So it's not smart, right? It's dumb, okay? But if you did dumb, then every time you come back, this random stuff keeps going on. And what I'm saying, the way to think about this is to think about, as usual, you would say, let x be the time. And then you want the expected value of x. And you write this down, but think of doing it. It's a recursive problem. Think of defining the answer in terms of what you want. So you're going forward. With probability 1/3, the answer is 2. With probability 1/3, it's 3 plus starting over. This is where the recursive part is. Right? I mean, I start, it's 1/3, it's 2. It's 1/3, it's 3, plus I start over, so it's just whatever it is. And then this will be 1/3, 5 times this. So now you just solve the equation for the one unknown. That's just a point of view that's often what you want to do. You create an equation. If the thing's going on, you create an equation that produces a solution, right? So now you see this is an equation in one unknown. Algebra remains only, right? Is it, if you do this, you'll see this is 2/3 plus 3/3 plus 5/3 on the right-hand side. But then you'll have a 1/3 and a 1/3, so this will turn out to be this when you rewrite it. And you'll see that, yes, expected time is 10. Right? Yes? Now, it's possible that I would totally screw this up and nobody would say anything. So, if I do my arithmetic wrong, save, okay, so it looks okay, although I often see the faces don't look happy. So this is 2 out immediately, 3 and come back and start over, 5 and come back and start over. And then just solve the equation. So I just did this just says the equation solves to this. Okay. 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 Well, this equation business is a good thing to think about, especially when things go on and on. So you reduced it to this reduces a very simple calculation where you're using the recursive, where you're using this in defining what you want. So it's a good thought process. And you don't want to, this is not getting you anywhere. That's sort of the thought. Okay, now, let's see. I have in mind 2 problems, which is just, that might be pushing it, but let's see. So we got these doors. Okay. Well, let's see. So now we have a problem where 2 CVN students have decided to come to campus. And they've decided to meet here in Mud. And that's Adora and Joe have decided to come to campus and meet at Mud. And they're going to, they decide to meet between 5 and 6. So they're going to meet and go out to dinner. But they're going to go out to dinner at 6. And they're going to meet between 5 and 6, except they make a peculiar kind of, they have a pattern. So let's suppose that they arrive independently. They come from different places. So it's between, they arrive independently and randomly, and in the interval between 5 and 6, which we can also call between 0 and 1. And let's suppose that they have the following policy, that they wait. The policy is they come at random, and let's let them come uniformly distributed at first. So they come sometime uniformly in that interval. And here's the question. The question is, what do? Their policy is they'll come and they'll wait 20 minutes. And if they don't, the other one isn't there when they arrive or after the 20. So the other one might be there when they arrive because they're each going to wait up to 20 minutes. But after 20 minutes, they're going to leave. So they each come and they each wait up to 20 minutes for the other one. So, I mean, you could say, what's the probability? So one question is, what's the probability that they don't meet? And then you start to think about, well, conditioned on the fact that they do meet, what's the expected amount of time they wait, and so forth. And if that isn't more interesting, we can make them arrive in some other pattern, that they don't really arrive. Maybe they arrive, let's say they're more likely to arrive, the density might look like this, so that they might more likely arrive toward this, and so then the density would be 2t. Right? Is that the right thing? Yes, because it's the density should be non-negative and integrate to 1. So this will integrate to t squared over t. Right? So this is the right between So they're more likely to arrive here. So this might change things. They could each arrive according to this density instead of uniform. But let's first do the case of the uniform. So they're arriving uniformly. We'll just take between 0 and 1 in a 1-hour interval. And they each will wait up to 20 minutes for the other. And so what's the probability that they don't meet? Okay, that's... Now, one part of this is well, they're arriving uniformly initially. Uniformly, that's continuously. So again, the probability that any of them arrives at exactly in the middle at any point, any particular point, is 0. And yet they have a density. So we're doing this is again a calculus problem. So it's a calculus problem, and the question of where they meet. And I guess the point here is, again, in a lot of these problems, a thought is to draw a picture. Try to think about the thing in a way that helps you by drawing a picture. So, I guess I'm thinking the obvious picture is the square. And then figure out where they meet, right? And when they meet and when they don't meet. This is... Adora arrives here, say, and Joe arrives here, and what places in this square, where are the points where they meet and where are the points where they don't meet? And that's sort of like you think about it, you don't just kind of go right to the answer, but do something thinking about it and it'll become easy. So you think here, well, if you wait 20 minutes in terms of hours, that's a third. So if... here's a third here, right? So they will meet. If Adora arrives 0 and Joe arrives in this interval, they will meet. And then as you go down here, you think there's this, and then the same thing, 1/3 here. And they meet in here. And I guess the way to see that is you pick some point here, x, and here's this x, and this is the diagonal, so this is x over here too, right? And so they meet if this is a third, if Joe arrives 20 minutes before that time or 20 minutes after. And then of course if it goes outside the interval, there's no help. It doesn't work. But if you were inside the interval, that means at each point this line would be 1/3 down and 1/3 up. And so then this region, it's drawn kind of not, doesn't, this should be, I'm drawing this right, should be 1/3 up. Let's see if I'm drawing this right. This should be 2/3, and this should be 2/3, for counting this way, right? The picture doesn't look too good. But they don't meet in these two triangles. So I guess the thought is, well then, if it's uniformly distributed and they're independent, then the distribution in the square is uniform. So then you're just thinking, what's the area of these two rectangles? This is 2/3 by 2/3, so that's 4/9. Divided by 2, but there's 2 of them, so the 4/9. So probability don't meet equals don't meet is 4/9. Right? That's the area of these two rectangles. 2/3 times 2/3 divided by 2 times 2. Now, suppose this is where the calculus comes in. Suppose they each had this, they arrived according to this density. They each arrived according to the same density, independent. So you would have the same problem. This is back to calculus, multivariate calculus, where you have to integrate over these triangles. So, what would we have written down? Probability don't meet. Okay, so we want to do one of these things, and you could see that you want, so if we do this, we're doing from 1/3 to 1, and it's 2t dt. Now, but we have another part, that's this way. We then want to consider this. And so we're integrating one variable this way and the other internal variable this way, and this is slope 1, so it's 1 minus 1/3 x. Let's see. So at 1, it's 2/3, and at 1/3, right? So this line is, I got that right? 1 minus 1/3 x, or right? So at 1/3, when x is 1/3, y is 0. When x is 1, y is 2/3, right? Okay. So that line is here. And then there's another one of these, 2u du. So this is the density, I'm assuming. And I have an outer integral and an integral, and I'm just doing one of these things. And I want to have two of them, right? I have two of those, so they're symmetric. I have two of those, and I've set this up. Did I do that right? Or let's see. So let's see. That sort of looks. That line. This doesn't look right because wait. Is this? This is. Okay. If it's x is 1/3, it should be 0. So this is not right here, right? This is. Am I doing this? This is slope. So t minus slope 1, right? So okay. So when this variable t is 0, I've got t is 1/3. So I've got should be t minus 1/3, huh? Right? Is that better? T minus 1/3. So when t is wait now. Did I do that wrong? Okay, this thing is 1/3. I'm 0, and when I'm here, 2/3. Yeah, this looks better. Does this look better? I'm thinking I'm going in my version. I'm having t go here, the outer variable, and u here, right? So then I've got this. And then when I do this integral, I'm going to get u squared between t minus 1/3 and 0, right? And we do this stuff, and I produce a polynomial.
Why do you multiply by 2?
2 because there are two of these rectangles, right? Two of these triangles. I maybe have to be careful. I have to be careful. I'm using symmetry. It's okay. I'm using symmetry that they're the same. Better be careful that they're the same. Absolutely. But I'm doing 2 because there's two triangles, and I've just integrated over the two triangles and so forth. So the point here, I guess, there's 2 points to this. One point is draw the picture, right? That's sort of really, and if it was uniform, it would be easy with the picture. The other point is, well, this is fundamentally basic multivariate calculus. Integrate the density over the region in the plane. So that part is but then knowing the definition. So some part you got to get the right stuff, set up the problem right, but when you do, you're going to be left with calculus. So I'm thinking the point here is if I write down the probability they don't meet, right, conceptually, if A is this and this, these two triangles, the probability they don't meet is the integral of this joint density over these two triangles. And since under the extra assumptions I made, that becomes this. Because I'm assuming that this is really f of x, f of y, because they're independent. So the joint density is the product of these two, and I've written it down. And I've written this over A carefully to do the two-dimensional integral. Struggling to do it. Okay. Are there... Yeah, I think that we would mercifully not do... I will start my next problem, and we'll discuss it Thursday. So that's... my next problem is... that's not bad. That's fair enough. I will not try to discuss this. So the next problem has to do with if you came from New Jersey. If you came from New Jersey like I would have a while ago, but not now, suppose that you have a lot of time on your hands because you're on a New Jersey transit train in a tunnel under the Hudson waiting for the Amtrak train that's disabled. And you're there for a long time, so because you're really excited about probability, you take a coin and think this is your opportunity to flip a coin a lot of times and see if it really is, if it's a probability of a coin coming up heads is a half. And you just feel that this is just what you need to do. It's the time, just the perfect time for it. And so you flip the coin 1,000,000 times, 1,000,000 coin tosses. That's my story. One might consider whether that's reasonable or not. But anyway, so you're flipping the coin 1,000,000 times, and then actually this was my experience. So I'm going to tell you possible things I'm going to do. I'm going to tell you I did this. Well, you can think it's crazy, okay? But anyway, I did this. And I'm going to tell you how many heads I got. And then you're going to have an opinion about it. So here's possible. I have 6 possible answers that I could have told you. Did I get 1, 2, 3, 4, 5 answers ought to be enough. Gee, 598. Okay, 5 answers is enough. So I've told you one of these. And the question is, the question is, what do you think about this? I mean, what do you think about these possible answers? Maybe the point is, how likely is it that those are true reports of my, first of all, assuming that I would toss the coin 1,000,000 times and I did it, whatever, and then I might report that I got this many heads. And the question is, what do you think of that? Okay, that's the question. And so the question sort of is like, how likely is that outcome? I mean, what are these outcomes? Does it sound like this is reasonable? And I guess I'm assuming, my point of view is that actually tossing the coin, the probability of heads is about a half. It's essentially a half. So then if I did this and I did it properly, are these reasonable outcomes? Okay, and that sort of, so in this time, actually, in the 2 minutes we had now in this time, you should be able to resolve that. Okay, that should be, you should have an opinion about all those things. It should be easy enough for you to look at that and resolve these. But we'll come back to this. So 500,000, 500,000, 312, 501,013, 511,060, 598,372. Do you have strong opinions about any of these? I mean, yeah. Yeah, this seems very unlikely. Number 4 sounds good. Any other thoughts?
I don't think 500,000 is very unlikely.
Yeah. This is. I think this is a very important observation. Again, it's a subtle point. Subtle point which requires some care, right? Because if you did this experiment and you took a coin that had exactly probability a half, and you asked which outcome is most likely of all the outcomes, you compute all the probabilities. this probability will be the largest, the most likely. And yet you're totally correct, right? Because even though this is the most likely one, it is very unlikely. And therefore, when this exact value is actually, this is where things are tricky. Very important. That's, of course, why it's here. So you've jumped to what perhaps the main observation. It's like the three doors with the game show, right? There's other things going on. Even though this is the single most likely outcome, it's not likely. And if you were told this, you wouldn't believe it for a second, right? And that's totally reasonable attitude. And if you found the probability, it's going to be small. I mean, it's going to be like 1 over, this particular outcome is like 1 over 1,000 or 500 or something, like that. It's very unlikely. But it's got the largest probability, and yet it's unlikely. And that's a reasonable reaction. So then, this and this, the last two on the boundaries, in my mind, are very strong. You just look at this and you say, no way. And you look at this and you say, no way. For slightly different reasons, but you say, absolutely. Then these three, this is where you need to think a little bit. That's the point where you maybe even need to calculate. Okay? And we'll talk about that. So you can think about that a little bit, but we'll do that on Thursday. So hopefully, I encourage you again to consider going to the recitation at 1. It's 1127 room. It's way up in the top, 1127 at 1 o'clock.